So here's a quick reminder of what is entailed in tagging problems. So abstractly, the tagging problem is to take some sequence of words, or letters in this case, as input, and as output produce a tagged sequence, where each element in the sequence now has an associated tag, for example C, D, C, and so on. One of the very first examples we saw was part-of-speech tagging. So in this case, the input is a sentence, and the output from the tagger is a tagged sentence, where each word now gets a tag. For example, profits is tagged as an N for noun, sword is tagged as a V for verb, at is tagged as a preposition, and so on and so on. A second crucial example we looked at was the problem of named entity recognition. So in this problem, again, the input to the model is a sentence, a sequence of words, and the output is a tagged sequence. The tags now encode the named entities found within the sentence. So for any word which is not an entity, we have this tag NA, whereas for words which are the start of a company, we have the tag SC. For words which are the continuation of a company, we have this tag CC. And similarly, we have start location, continue location, start person, and continue person, and so on. And we've seen two basic models for tagging problem, hidden Markov models, HMMs. And more recently, we saw log linear taggers. So those are the first two methods we've seen. In this lecture, we're going to see a third method, which is how global linear models, GLMs, and the perceptron can be applied to tagging problems. So how are we going to set up this GLM for tagging? Okay, so as input to our model, we have some sentence. So let's say n equals 3, for example. We might have a sentence W1 through 3, which is equal to W1, W2, W3. We might have some sentence like the dog barks, for example. Now, define T to be the set of possible tags. So let's just assume we have three part-of-speech tags, D and V. The first thing we're going to define is the function gen. So remember, gen is going to take some sentence as input and map it to a set of candidate structures. And in this particular case, we're going to use this definition, where gen, for any sentence, simply returns all possible tag sequences of length n. So in this particular example, gen of this sentence, W1, W2, W3, would be the set which consists of all tag sequences of length 3 using these 3 tags. And so on and so on. Okay, so there are actually 3 to the 3, that's 27 members of gen in this case. Okay, so gen is really the most simple function you could think of, which simply just lists all possible tag sequences for the input sentence. Now, critically, the size of gen is going to be exponential in the length of the sentence. So in fact, the size of gen for some sentence x is going to be the number of possible tags. So this is the size of the set T, that's the number of possible tags, raised to the power n, where n is the length of the sentence. Because I have T possible tags at the first position, T possible tags at the second position, T possible tags at the third position, and so on and so on. So if you think about global linear models, as we've presented them so far, the algorithms we've looked at have had to explicitly enumerate all of the different members of gen and score them under this function v.f of xy. And this clearly isn't going to be tractable for this definition of gen. Once n gets to any appreciable length, the size of this set will simply be too large for us to brute force enumerate all of the different elements of this set gen. What we'll see, though, is that under a particular definition of our function f, things work out. We can actually apply global linear models in an efficient way. And this is what I'm going to talk about next.